What we can also look at is the irreversibility. We looked at the extent of irreversibility earlier in the case of systems. We can also look at it in the case of control volumes. So the irreversibility is essentially whatever is the work you would get if the process was reversible minus whatever is the work which you get in the actual process. And we have seen from the earlier expressions that if you take the subtraction of these two, it essentially comes out to be q dot reversible, because in the work the extra term due to the reversible process is essentially this term. So this is essentially the extra amount of work we get, and that is also equal to T naught into S dot generated in the actual control volume. So we see that this is the amount of irreversibility. This is essentially what we are doing in increasing the entropy, and this is the amount of work which we would lose when we have a process which is running irreversibly instead of in a reversible fashion. We can also look at the unsteady process for a control mass. So we had the equation earlier, which we just derived, which showed us the work done in the case of a control volume. So if we take that equation, it's a general equation, and if we put m dot in and m dot out, m dot inlet and exits as 0, because we have a control mass and there's no more flow coming in and out, so whatever terms are left, those are essentially the unsteady control mass process. So we see that in that case, w dot reversible, which is over here, would be sigma of 1 minus T naught by Tj into Qj dot minus of whatever is the change in the energy of this control mass with respect to time, minus of T naught into whatever is the change in the entropy of this control mass with respect to time. What we can also do is to integrate this from state 1 to 2. We could also integrate it in the case of the control volume if we knew enough things about the state of the mass and the entropies and enthalpies and so on. But in the case of the control mass, it's a lot easier to integrate. So we can integrate it directly, and then what we see is that this is essentially 1 minus T naught by Tj into 1 Q2 minus of the change in energy with respect to time is E2 minus E1 minus T naught is a constant, change in entropy with respect to time when integrated gives S2 minus S1. So we get this expression to tell us how much of work we can get if we had different sources Qj's going from state 1 to 2, when the energy changes from state 1 to 2 and when the entropy changes from 1 to 2. So we can use this to find out how much work we can get in a reversible process. We will also define what is called as a dead state, because we are looking at Exergy, which means that there is a reference environment, which means that we need to define what happens when we get the maximum work. So we can get the maximum work when we finally reach equilibrium with the reference environment. So equilibrium essentially means it has to be in mechanical equilibrium, it has to be in thermal equilibrium, in chemical equilibrium, and so on. So this object should finally be at rest. We don't want it to have a higher temperature, because if there was a higher temperature, there would still be scope for transfer of energy, which means we can still convert it to work. If there were chemical reactions taking place, then maybe we can still extract out some work from it. So if we cannot extract any more work from it, it should be in mechanical, thermal and chemical equilibrium. If the object is still moving, we can use its kinetic energy to do work. Therefore, if we are to extract maximum work, the object should no longer have any kinetic energy. If it was a control volume, when the inlet has kinetic energy when it flows in, ideally if we are to extract all the possible work we can from it, the exit should have no kinetic energy. But we see that that is not really a feasible thing, because if there is no kinetic energy at the exit, it means velocity is 0 at the exit. So if you have a control volume in which the velocity is 0 at the exit, it means no mass is leaving that volume. So that is definitely not feasible. But what we can at least think of is that the kinetic energy or the velocity at the exit should be very, very small. So we need to slow down the gases or liquids going through the control volume so that they go out slowly, because only then can we extract most of the work from it. Similarly, if the potential energy of the system is high compared to the ground state, then it means that the system can still be lowered and we can extract energy. Therefore, we should have the system at the ground state if we have extracted all the energy from it, and that is our dead state. And if we are having a control volume where fluid is coming in one inlet and going out, say, in an outlet, what we would expect is that the outlet is at the lowest possible place, so that the fluid going out of the control volume does not take potential energy away with it. So if we can have all of these, then it means that we have extracted whatever we can from the system or the control volume, and that is the case in which we can get the maximum work from whatever we have. So we can look at what is called as flow exergy, where we look at a control volume with a single inlet and a single outlet, really speaking. But at the ideal case, as we said, we expect that at the outlet things are at the dead state. Let us look at a control volume without any heat transfer. The exit of this control volume is a dead state. So at dead state, our kinetic energy is 0. The velocity of fluid going out is very, very close to 0. The kinetic energy is 0. The entropy is whatever is the entropy of the substance in the surroundings. The enthalpy is the enthalpy of whatever is the surroundings. The height at which this liquid goes out is at the ground level. So if we have all of this, then we can extract out the most work from the fluid which is going into this control volume. So from the expression we just had, we have W reversible is W dot by M dot, which is sigma into 1 minus T naught by Tj into Qj plus enthalpy, kinetic energy and potential energy at the inlet minus entropy times temperature at the inlet plus reference temperature into entropy at the inlet minus enthalpy at the outlet, kinetic energy, potential energy outlet minus reference temperature times entropy at the exit. So what we see is that in our assumption we say there is no heat transfer, therefore this term marked in red has to be 0. So if you look at the reversible work, we see that we have this entire term as it is. From this term, what we see is ideally we would like the enthalpy at the exit to be whatever is the reference enthalpy. So this becomes H naught. We would like the velocity to be 0. So we don't want any kinetic energy to go out. So therefore this term is 0. We would like the height at which this substance goes out to be at ground level. So the ground level is whatever is the ground level at that place. So for example, if you are in Bangalore, the ground level is several hundreds of meters higher than if you are in Chennai. So with respect to the local ground, whatever is the level of the ground, we want Z to be that. So instead of Z as being at exit, we want it to be at the level of the ground locally. And we want the entropy to be whatever is the entropy of the surroundings locally. So instead of SC, we have S naught. So if we have all of these terms in this way, then we can get the maximum work from the fluid which is going in. And this is essentially what we call as the flow exergy. So exergy for a control volume undergoing this kind of a process. And what we also see is, this is the maximum work we can get from this fluid going in. But we can also, if we want to know in a real process what happens, we can also use the exergy of the fluid going in, the exergy of the fluid going out, and find the difference in it to find out what is the reversible work. So for example, what we see is if I had at the inlet psi I would be essentially this term. If I was to look at psi E, I would have E over here, over here, over here, over here, and all of these are essentially the same. So if I was to subtract psi I minus psi E, I will essentially get this term minus the same term at the exit, or essentially I would get whatever is over here. So in order to find out the reversible work, what I can do is I can find out changes in the exergy. Instead of looking at the energy equation in this form, I can find out changes in exergy. Of course, we are looking at only a case which does not have any heat transfer. In those cases, I can look at changes in exergy between the inlet and the outlet, and that will give me how much work I can get. So that was for a control volume. Now for a system or a control mass, we can similarly find out an expression. So we start like before from the control volume equation. And what we can do is, we can consider that the volume can change, because we are going to look at a system. We usually have boundary work in the case of systems. So we will assume that the control volume can change. The volume of the control volume can change, and it can do work against the surroundings. So the work done against the surroundings is the rate of doing work is called W dot surroundings. That's essentially P naught, which is the pressure at the boundary, the atmospheric pressure in most cases, into V dot, which is the rate of change of volume of the control volume. So this is the amount of work which this control mass does against the surroundings. And what we can write is that W dot max available is W dot reversible and stored minus W dot surroundings, which means that the maximum work we can get, we can actually substitute for whatever is stored from the previous expressions which we had, which is essentially change in energy with respect to time minus T naught into ds Cv by dt. This was earlier there in the expressions of maximum work for the control volume which we found. We didn't use it in the last 2 slides or so because we were assuming things to be steady. But if you have unsteady, these are the terms which are there. And then we have whatever work is done against the surroundings, which is essentially P naught into V dot, which is from here. So we have this expression. What we can do is we can integrate this, and if we integrate it, we get the maximum work which is available to us, or which we can do, which is essentially what we call as the exergy for the control mass, or the exergy for the system, which is essentially minus of integral of this is E naught is the final state, because the final state is the dead state, E naught minus E. We have minus T naught. The final state for this is S naught, so the integral of this is S naught minus S, and we have plus P naught into V naught minus V. So if we rearrange this, we have this expression in this form, and like before, we can use differences in exergy and also differences in specific exergy to get the work done between states. The specific exergy phi is defined as this thing by m, so essentially small e minus T naught into small s plus P naught into small v minus E naught minus T naught into S naught plus P naught into V naught. So this is what we have. One of the things we should note is that exergy is defined for a system and the environment together, because it depends on what are the values of the pressure and temperature and so on of the environment at that place. So the exergy would be different for the same system if the system is in different environments. So it is a property of system and environment both put together, and you cannot look at it as only for the system or only at the environment. A second thing we should note is that the exergy cannot be negative. The third thing we should note is that exergy is not conserved. So what we see is that in our expressions for exergy, we have entropy terms which are there, and as the entropy increases, what we see is that we are actually destroying the exergy. So exergy is not conserved, and it will keep reducing as we are doing work or as we have irreversibilities and so on. And we defined it as the maximum work we can obtain in going from the present state of the system to the dead state. What we can also define it as is the minimum work we have to do in order to take the system from the dead state to whatever its state was. So both of them are equivalent. So the maximum work you will get is essentially when it is reversible. When you are going from its present state to dead state, maximum work you will get is when the process is reversible. In a similar fashion, what we see is that if you want to change the state of this system from a dead state to any particular state, the minimum work you will do is when it is reversible. So the minimum work input which you have to give is also the exergy when you are going from the dead state to whatever is the state. So what we will do now is to look at an example. I don't have all the numbers worked out here, but I have noted down all the steps, and I think you should be able to go on and do it. So here it says, determine the specific exergy of water vapor at 170 degrees centigrade when the quality is 0.7. The water vapor has a velocity of 50 meters per second at a height of 10 meters above the ground, it's supposed to mean, relative to an exergy reference environment at 25 degrees centigrade and 1 bar. The acceleration due to gravity is given. Properties of liquid water are given, are tabulated here. So what we are asked to find out is the specific exergy. So the problem we have is a specific quantity of water vapor. The mass is fixed, therefore we would treat this as a system. The dead state is given as 25 degrees centigrade, and the temperature of the dead state is 25 degrees, which is 298 Kelvin, and the pressure is 1 bar, which is P naught, 1 bar, which is 0.1 megapascal. The dead state would be the ground, which is at rest. And for the initial state, what we are given is it is 170 degrees centigrade and a quality of 0.7. So therefore it must be on the saturated saturation curve. It must be on the saturated line because it has a quality. So it's between the liquid and the vapor lines. The velocity of the steam initially is given as 50 meters per second. The height initially is given as 10 meters above the ground. So, and the substance is steam. So this is all the information we have. So what we can see is state 1 is saturated. So I have just pulled out the line corresponding to 170 degrees. So this is temperature. This is the saturation pressure in megapascal. This is Vf, Vg, Uf, Ug, Hf, Hfg, Hg, Sf, Sfg, Sg. You have the steam tables with you, so you can look at the corresponding line on it anyway. What we are asked for is the exergy, the specific exergy, which is phi by m, which is what we are asked for. It is defined as E minus T naught S plus P naught V minus of E naught minus T naught S naught plus P naught V naught. So all we need to do is find out all of these values and substitute them. So as far as this values are concerned, E, S and V, these are the initial state, which for us is 170 degrees saturated steam with a quality of 0.7. So E is the total energy, which is the internal energy plus kinetic energy plus potential energy. The internal energy of steam I can find out from the tables. So U is essentially UF plus X into UG minus UF. So that's UF plus X into UG minus UF. These tables have units of kilojoule per kg. I am going to add them to kinetic energy, which I will use in meter square per second square. So I need to make sure I multiply by this factor of 1000 over here. Kinetic energy is V square by 2. The velocity of the steam is given as 50 meters per second. So that's 50 square divided by 2 or into 0.5. And potential energy is G into Z. G is 9.81 meters per second square into Z is 10 meters. So I can calculate this. I will encourage you to do it and you should get an answer for this. It will have units of either joule per kg or meter square per second square. So this calculation gives us essentially this term. The next term is T naught, which is 298 times S. Again, S is calculated at the initial condition of the steam, which is 170 degrees centigrade and 0.7 quality. So S would be essentially SF plus X into SFG. So that's essentially SF plus X into SFG. We can find out this value, multiply it by T naught, we get this. And the third value is P naught, which is the reference pressure, which is given as 1 bar into the specific volume. And again, this should be actually small v. It has been auto capitalized. So small v is essentially Vf plus X into Vg minus Vf. So that is Vf plus X into Vg minus Vf, and we can get this value. Multiply that by the pressure in pascals, and we should get something in joule per kg. So up to here we have looked at this term in its entirety. What we need are these values. So E naught corresponds to water at the reference conditions. So the reference conditions is 298 Kelvin and a pressure of 1 bar. So at a pressure of 1 bar, when you look at the steam tables, we see that the corresponding saturation temperature is about 99.6 degrees centigrade. I don't have the tables open here. You can look at your steam tables. At a pressure of 1 bar, we see that the saturation temperature is about close to 100 degrees centigrade, which means that at a temperature of 25 degrees centigrade, which is what is given over here, the temperature is much lower than the saturation temperature at that pressure. So we are at a much lower temperature compared to boiling temperature at that pressure, which means that the water is going to be in the subcooled or compressed liquid region. It's going to be on the left of the two-phase dome. So, and we are quite far away from the dome. So the best thing to do in these cases is to look at properties of water from tables. So we had not shared the liquid water tables earlier. Now we see that we need them for this case, and they are given for this question over here. So what we need to do is to find out properties at the condition of the reference or dead state. which is 25 degrees centigrade, and 1 bar. 1 bar is 0.1 megapascal. We see all of these correspond to 1 bar. We need them at 25 degrees centigrade, which is essentially these values over here. So what we need are the specific internal energy, which is given as 104.82. So E naught is 104.82, that's in kilojoule per kg into 1000 joule per kg or meter square per second square. This is U naught, plus I need potential energy at the dead state. At the dead state, I know that the steam should be on the ground, so potential energy at the dead state is 0. I need kinetic energy at the dead state. I know that kinetic energy at the dead state should be 0 because the substance should be at rest. So these should also be 0. So I would get the value here as 10482. And then I need S naught because I need T naught into S naught. So S naught again corresponds to entropy at this condition. So at this condition, we can see the thing is completely liquid. So we can just directly take values. We don't need to do, there is no quality associated with it. So our entropy over here is essentially 0.672 kilojoule per kg Kelvin. So we can take it as 0.3672 into 1000 joule per kg Kelvin. And then we need plus P naught V naught. P naught is 1 bar, 10.5 pascal. And we need V naught, which again looking at this is 0.001003. So if we multiply it by 10 power 5, we see that the value would be 0.01 joule per kg. So having all of these values, we can substitute into all of these and we should be able to get the value of the Exergy in this case. So whatever is the Exergy value will tell us that supposing this steam was used in a reversible process and it was brought to the dead state, that is the amount of work we would be able to extract from this. What is also usually interesting in these cases is to compare the contributions of different terms towards the Exergy. So this is the total Exergy. We can look at, for example, E minus E naught, this term, T naught S minus T naught S naught, and P naught V minus P naught V naught, and see, and also we can look at, for example, in the energy term, we can look at also specific contributions from internal energy, kinetic energy and potential energy, and it gives us some idea of which of these terms it gives us the most amount of work, and that is quite interesting sometimes to see. And what we also see in these cases is that if we had, for example, only like say potential and kinetic energy and so on, then we can do the processes more reversibly and we do not have any entropy contributions. If I have a reversible process which involves say a block or something like that, or a liquid, the entropy contributions typically may not be very high at all. So, and if I had like say only potential or kinetic energy and I did a lifted or raised a block, then what we could see is that in such a case the process would be more or less frictionless if I ignore air friction and if I have a pulley without any friction and so on. So in those cases I do not have essentially any loss of Exergy because the process is reversible. So I'm going to stop here for now, and maybe we'll give you a few more problems on Exergy in the assignment which you can work out. Thank you.